So I'm going to be talking about something that is part of a large DOE-funded Energy Frontiers Research Center. And you can see down here in the lower right all of the institutions that are involved in it. This is a large collaboration between theory and experiment. Obviously, we're handling the theory part of it. Um, and just to sort of anticipate how this talk is going to go, in the beginning, I'm going to talk more about bulk phase charge transfer reactions and how we can understand them. I'll be kind of jumping back and forth between the physical chemistry part of this and the methodology. And then toward the end, when we sort of look forward to the sorts of techniques that we would like to bring into the project, I'll focus more on sort of newer methodology that we're actually quite excited about. And at that point, we'll also talk more about things that we're doing to handle the interfacial problem. So I hope all that makes sense. The kind of technology that we're focusing on here is the so-called redox flow battery. And in this kind of battery technology, you've got your electrolytes in these tanks, and you pump them into the electrochemical cell, as you see here, where all the electrochemistry magic is happening, all the charge transfer reactions are taking place, and our goal is to develop novel, what we call breakthrough electrolytes for use in this kind of battery technology. And I want to kind of convince you of the important role of quantum mechanics or quantum effects in what we're looking at. Okay, so let me first just begin by acknowledging the collaborators on this. So our center is run out of Case Western. Our director is Bortsu Gurkan, but I'm also working with researchers at Hunter College, Steve Greenbaum, Joshua Sengoro at Ohio State. So Steve is doing NMR. Joshua is doing dielectric spectroscopy. Mark Dadman at Case Western, who's doing work on quasi-elastic neutron scattering, and a host of really good students and postdocs. And some of the work I'll talk about is also being done in collaboration with my colleagues at NYU Shanghai, Shangsun, and Sunghui Liu. And then there's a portion of this which is now being funded by the Einstein Foundation in Berlin, where I'm spending a couple of months every year for the next few years. All right. So redox flow batteries are incredibly scalable. Here's an example of a little tabletop experiment that you can make for one of your PChem labs, all right? And you can see the electrolyte tanks and the sort of workings of the battery, the pumps that are, connected to the cell by these hoses. But you can also have really big sort of power plant size redox flow batteries for energy storage and deployment. The problem with a lot of these technologies is that they use crucial metals, all right? So these are kind of based on things like vanadium oxide. You've got possibly lithium and cobalt. Oh, by the way, you can also have the redox flow car battery, by the way. I wanted to point that out. The goal here is to get away from these crucial metals, because if you want to scale this kind of technology up so that everyone's using it, you're not going to have enough of these metals available for the supply, the demand that would need to be met. So what we're trying to do is to go toward simple organic compounds you can easily make in the lab. And normally when we think about these organic compounds, we think about ionic liquids. Okay? And a kind of typical example of this is the deep eutectic solvent ethylene glycol chloride, which is a truly ionic system. It looks like this. You're looking at a little molecular dynamics movie of this ethylene glycol chloride mixture, which is also known as ethylene for short. And the problem that these ionic mixtures have, you can imagine, is that if you compare viscosity and conductivity plots, you see there's a very clear inverse relationship. As I decrease the temperature for different compositions of this ethylene mixture, you can see that the viscosity is going up. And this is true whether you're computing these things using Green-Kubo relations or you're measuring it experimentally. And this is accompanied by a corresponding decrease in the conductivity, right? So to be at temperatures where you might really want to operate, you're going to be facing this issue. Now, there's an empirical rule that's known as Walden's rule that predicts that this is the kind of thing that you would expect to happen. And it shows this inverse relationship between conductivity and viscosity. And this is very limiting in the kind of performance that you can expect. So our strategy has been to look for a wider range of systems that we call concentrated hydrogen bonded electrolytes that can support different kinds of charge transfer mechanisms. And what we're focusing on here are mechanisms that we learned about from studying fuel cells, and this is the so-called Grotthuss charge transport mechanism. And this mechanism goes all the way back to this very old paper you can see by Lithuanian chemist Christoph von Grotthuss. And as you can see, in 1806, this was a time in scientific history when the bulk of scientific papers were being written in French, and you see that here. And what he was doing is he was electrolyzing water. So he was looking at water electrolysis and measuring the currents that you get. And the currents that he was getting were larger than he could explain by a kind of simple vehicular mechanism where you imagine there's an ion and it's got a solvation shell around it and it's being carried along vehicularly with its solvation shell. All right. Now, in 1806, of course, Grotthuss wouldn't have known that water was H2O, right? The atomic theory was brand new at that time. But even without knowing this, he had the idea, it's very crudely illustrated in the paper, but that there is a kind of hopping mechanism where something is being passed from one species to another that doesn't require this vehicular mechanism. And if he did know what water was, he might have envisioned it something like this, all right, where you see that there's a hydronium ion, it's got an excess proton on it, and this thing is being moved from one place to another along a string of hydrogen bonds via a proton transfer reaction. So this is what's known as the Grotthuss mechanism. Now, this little cartoon that you see here, which you can find on Wikipedia, is a total falsehood because this is not the way things happen in water. Water is a much more complicated liquid, and although there is Grotthuss shuttling, it happens via complex rearrangement of hydrogen bonds. But in the world of organic liquids, there is a system that kind of does behave this way, and it's imidazole. So imidazole is a very simple, light, organic molecule. You put an excess proton in there, you get this thing called imidazolium. And I have a little movie of this. Let's see if I can get this to work. There we go. Okay. So the imidazolium is the one with the two gold hydrogens on it. And you can see that what's happening is there's a proton transfer reaction that moves the imidazolium from one place to another in what looks like a kind of quasi-linear chain of hydrogen bonds. Over time, you get net displacement of this imidazolium species. Now, the way this is being done, let me get my pointer back. The way this is being done is we use what's called ab initio molecular dynamics, right? So you're calculating the electronic structure on the fly as this simulation evolves. And this is motion on the ground state Born-Oppenheimer surface. Of course, we don't do this exactly as this equation would suggest. We do this within the Cohen-Sham density functional theory approximations, and we're using GGAs and D3 dispersion corrections to do it. Now, what you do find from this trajectory is if you look at the diffusion constants of imidazolium and imidazole, there's like an order of magnitude difference between them. And so this is the first indication that you can decouple the charge transfer kinetics from the underlying solvent dynamics. Okay, now it took about a year to get a trajectory long enough to get this using ab initio molecular dynamics. And I'm going to come back to this point because in order to collaborate with experimentalists, we need much better throughput than that. So our colleagues in the EFRC have done a bunch of measurements of conductivity and viscosity for certain imidazole derivatives, also triazoles, and then two proton suppliers, because these systems don't actually autoionize. So you need to put an acid in there, which could be either levulinic acid or acetic acid in what we studied so far. And you can see, for example, that the kinds of conductivities you're getting are ranging from, let's say, about 1 millisiemens per centimeter to 6 or 7, depending on which combination you look. So imidazole with acetic acid has a conductivity around 5 or so. Methylimidazole with acetic acid has one at about 6. These are all equimolar mixtures. The levulinic acid is down here at about 1. If you add a little bit more imidazole to it, you can get that conductivity more like up around 4 or so, right? And the big losers are the triazoles. I probably won't have time to get into why that is, but you can ask me about it later. But we want to understand, what is it that's giving rise to the conductivities that we're seeing? And I should, state at the outset that these conductivity ranges are lower than we would like, right? We would like to get the conductivity up by maybe at least an order of magnitude, if not a little bit more than that. We have some ideas for how to do that. I'll talk about that a little bit later. But we expect the basic mechanisms to be essentially the same. And so what can we learn just from studying these systems? Now, as I said, doing ab initio MD kind of requires a lot more computational time than we have, and we want to study all these different systems. So solving these equations, maybe we get a picosecond per day on a system of 700 atoms. So it can take a year to complete a trajectory long enough to get the dynamics out. So what we're doing is we're now bypassing these expensive electronic structure calculations with machine learning. And the approach that we're taking to this is to use so-called equivariant transformer networks, all right? The same kind of transformers that you have in ChatGPT, with the difference that instead of feeding in, language vectors that, encode language elements, we're actually putting in vectors, long vectors of interatomic distances, creating an embedding. Then the embeddings exchange information with each other. You create an attention weight for the different features. And finally, you get a way to decompose the energy, as you sort of expect, into different atomic contributions, which are sensitive to their neighborhood and surrounding neighborhoods. Okay, so equivariant transformers are incredibly data efficient, so we can get good training with about 300 snapshots, which we can generate in about a week using ab initio MD. We do this at the different concentrations, and once we have these things trained, we get about a nanosecond per day. This is a 1,000-fold speed up, and that means the throughput is now fast enough that we can really study a variety of different systems. Okay? Even if we increase the system size, we don't really hurt the performance that much. And because these things are so data efficient, easy allows for transfer learning to different compositions, or maybe we derivatize the imidazole. We don't really have to retrain that much in order to get a new potential working. So this kind of obviates the need for using foundation models, at least within this framework or this space of systems that we're looking at. Now, how well do we do? All right, so here's an example of a reaction profile. It's a free energy profile for the transfer of the proton from the acid to the imidazole. On the left is on the imidazole, on the right is on the acid, and you can see that this is an asymmetric double well with barriers on either side. The different compositions are 33, 50, 66, that's levulinic acid, versus these values for the imidazole. And that's what the machine learning model gets for the barriers, right? And you can see that you reproduce the asymmetric double well, and the barriers are in agreement with the ab initio and D2 within, just a few tenths of a kcal per mole at most. So this tells us that, this is a really kind of robust way of doing this. Okay, now, maybe I won't linger too much on this, but the math that underlies these equivariant transformers for doing the chemistry is really the same as what you have in ChatGPT, all right? As I said, we come in with these vectors of interatomic distances that are actually put into a set of radial basis functions. We create these neighborhood embeddings, and then you set up, your distance, your keyword, and your query vectors. You do the usual dot product between them to look at the overlap to see, how much particular query overlaps with your keywords. You set up the attention weight, and then you have your features that then pass messages through graph convolutions. It turns out, people can ask about this if they're interested, that this captures a lot of the long range effects that are otherwise often missing from these machine learning models. And we have evidence of that. Okay, so how do we get a good model? We do query by committee. So we start off with a random sample of initial training set, maybe 150 configurations. Then you have a committee of n different transformer networks, and you look to see if there's agreement or disagreement between them. All right, and if there's disagreement, you take high variance configurations and you reevaluate the ab initio energies for them, and you just go back and you continue to update your training and its sort of active learning process until you get to about 300 or so configurations, and usually by that time you've converged. Okay, so let's look at an example. Movie to work. I probably have to turn off my pointer. Okay, whoops. This is what happens when the machine learning model is turned loose on the mixture of acid and imidazole, levulinic acid. And the little bubble there is showing you where one of these protonated species is, all right? And you can see that it's basically migrating along a hydrogen-bonded chain of imidazoles very nicely. Everything stays together, which is kind of a miracle for these machine learning models. Now, I showed you these reaction profiles, and we saw the asymmetric double well for the transfer of the acid to the imidazole, and you can see that there's symmetric double well for transfer of the proton between the two imidazoles. And, these barriers tend to be between 1 and 2 kilocalories per mole. But we also know that when protons are involved, you have nuclear quantum effects. So the way we take this into account is to use the Feynman path integral, which, rigorously allows us to calculate any equilibrium property from the partition function. And the picture that you get from, this equation for the partition function is that every quantum particle is then replaced by a cyclic polymer chain with a set of beads that interact with the beads of another ring polymer through in this case, our machine learning potential. It does so index-wise around each ring polymer. And these springs are due to the quantum kinetic energy. All right. And the way you can sample this distribution is just to use simple Langevin dynamics, for example, as a thermostat. And when you do this, you get a real change in what these free energy profiles look like. So the barrier for imidazole to imidazole transfer goes way down below 1 kilocalorie per mole. It's almost negligible at that point. And the asymmetric double well is no longer a double well at all, right? Quantum effects turn this into a single well profile. So in other words, when the acids ionize, they give the protons immediately to the imidazoles where all the proton conduction happens. So this is a local effect, but it's an enhancement of the proton conduction by getting it to where it needs to go. All right. Now, of course, path integrals are always going into classically forbidden regions that we didn't train for in our potentials. So usually, you'll find that there are holes in your potential, and you might need to do a little bit of updating of your training with some additional classically forbidden configurations in order to get a nice correlation curve like this that shows that you can reproduce, your predicted forces. All right. So one of the things that now because path integrals are expensive, I have now these P replicas of my system, and typically we're using 20 or so replicas. So one of the things that we've come up with to improve the efficiency is to use the so-called ring polymer contraction method. Now, this goes back to work of Tom Markland and David Manilopoulos, and we recently published a work that extends it to things like open chains and different ways of transforming the beads. So the contraction transformation turns a full polymer chain into a contracted one, and the idea is that on the smaller chain, we'll evaluate a full set of forces, and on all of the beads, we're going to use or work with a cheaper model, all right? So, for example, we like to use what are called staging variables, and we can work out what this transformation is in staging variables. Other people like to use normal modes. You can do that as well. But the point here is that on the contracted beads, we're going to use the full long-range machine learning model that we've got, and we'll train a cheaper short-range model to be evaluated on all the beads. Now, that's going to be a lot cheaper, all right? And so short-range model has a cutoff, let's say, of 5 angstroms. Our long-range model has a cutoff of 8. And you can see that with ring polymer contractions, you basically save a factor of about 4, right? So although it is more expensive than the original MD, it's still a savings that benefits us greatly. Now, how good is the short-range model? If we look at some vibrational densities of states in these systems for different frequencies, you can see that the short-range model is not doing such a great job of reproducing these densities of states, right? But it doesn't matter. It doesn't have to be that good of a model. It just has to be reasonably good, but cheap, all right? And in this case, we can contract all the way down to a single bead where we're evaluating our full potential, and all the other beads are getting the short-range potential. So there's little overhead compared to MD, but not as much. Okay, so let's look at the experimental picture and then see how our model is doing. So these are measurements of viscosity, diffusivity, its green curve, and the conductivity for this imidazole levulinic acid mixture. Right? And what you see immediately is that as the viscosity increases and reaches a peak, the conductivity is also going up. Now, the molecular diffusivity mirrors the viscosity in that when the viscosity is peaked, the diffusivity is a minimum, as you would expect. But the charge conductivity is actually monotonically increasing. It has a slow rise through this kind of region 2 where the viscosity is rapidly increasing. But there at the peak, the conductivity really starts to take off. And though the viscosity comes down a little bit as this, you see the kind of the latter end of the increase of viscosity, it's still fairly viscous. Now let's look at what the machine learning model predicts. And to get these transport coefficients, we use what's called ring polymer molecular dynamics, where you just run the path integral MD, but without a thermostat, and then you use the dynamics of the beads to get correlation functions that we then feed into Green Kubo. And you can see that, the trends are nicely reproduced. We don't have as many points as they have in the experiment, and we're working on filling in some of the missing points here. But overall, you see the rise and the decrease, the turnover in the viscosity. You see the mirroring with the diffusivity and the monotonically increasing conductivity. So this gives us confidence that we can try to understand the mechanisms that are at work here. Okay. And so, first of all, we wanted to get a sense of what the structures are that are emerging as we increase the imidazole composition. And so we define a little free energy surface that allows us to define a hydrogen bond between 2 imidazoles. And when you do that, you use like a 2kT contour cutoff. What you find is that as you add more and more imidazoles, what's happening is you're growing these chain-like structures that are the conduits for the proton. And these chains can contain imidazole and acid. The acid can also work as a relay mechanism. But you also see there's a big difference between the chain lengths between classical and quantum simulations. Now, this is a kind of non-local quantum effect. And if I turn this into a physical length by looking at the radius of gyration of these chains, again, there's a difference between the classical and the quantum, the classical chains are coming up short, which means they're not going to be as conductive as the quantum ones. What causes this? It's largely chain polarization due to the quantum delocalization of protons. Now, this chain length that we get from the quantum simulations, something you can compare to quasi-elastic neutron scattering. So you look at the scattering curve and you take the peak and then you plug into, this little distance formula, and you find at 60% imidazole, you get about 13 angstroms, and that's an amazingly good agreement, maybe fortuitous, but a really good agreement with our quantum results. We can also, as additional verification, look at the trends in the static dielectric constant, which we get by looking at the dipole moment fluctuations. And you can see, for example, that as the imidazole composition goes up, so does the static dielectric constant, which in the experiments they measure by looking at this plateau. And we look at the variance of our dipole distribution. And although our numbers are not in perfect agreement with experiment, the trend is nicely reproduced, that this static dielectric constant is going up. Okay, now the other thing that matters here is the dynamics of these chains. So to analyze this, we look at the reorientation of the imidazoles by looking at this vector connecting the two hydrogens and looking at its reorientation. All right, so you look at this second-order Legendre polynomial of this correlation function, and that is something that you can fit to a set of exponentials. So they decay as you see here, and you take the longest time scale, so that's the tau 3, and if you plot it versus imidazole composition, well, you can see that there's now, again, more of a difference between the classical and the quantum. So classical has no real discernible pattern. It's up, it's down, it's up. But the quantum results nicely mirror what we saw with the viscosity. And so that's qualitatively exactly what we would expect. Now, what does this reorientation look like? So, if you look at a chain and you set a clock, let's say at t equals 0, and then you look a few hundred picoseconds later, there'll be some reorientation event that breaks one of the hydrogen bonds in the chain, and now the chain has a totally different composition. And it's the scrambling of this composition of the chains that means you cut off the backward path for the proton to return to its kind of original state where it was at t equals 0. And by constantly changing the membership of these chains, you get continued forward motion or transport, net transport of the charge this way. So you can think of it almost as moving stairways in, Harry Potter and Hogwarts, where as the stairways move, you're always, going to a different place. And this is what's happening here. Okay, just very quickly, we compare different chemistries, so that's with the imidazole levulinic acid. And if you look at imidazole with acetic acid, you do get these higher conductivities, which is kind of nice, but there's like a little dip in there that kind of mirrors what's happening with the viscosity. So maybe it's a little bit more Walden-like, but we can reproduce that dip with our machine learning model. And if you look at methylimidazole with acetic acid, you can see that there's like a window of low imidazole compositions where you get good conductivity. And that, let's see if I can again get my movie to work. Okay, so this is a movie of what's happening in that system. And what you see there is when you methylate the imidazole, you cut off one of its hydrogen bond sites. So all the proton conduction now has to happen through the acetic acid, which is able to form these chains as well. And so you see the protons being passed from one acid to the other, but probably being ordered by the presence of the imidazole. It just takes a small amount to do this. Okay. Now I want to maybe talk a little bit about charge transfer. All right, so electron transfer. And so for this, we've been looking at some redox-active molecules that were suggested by our experimental colleagues. And we just wanted to get a sense first if there was reversible proton transfer back and forth between the imidazoles and these redox-active molecules. And so they suggested these compounds here, and when you look at the reaction profiles, I'm sorry, this is a little bit small, but the minimum that you see here is the proton on the redox-active species. And these things are all single minimums. So the proton is never given back to the imidazole. In other words, you don't have reversible proton transfer. Okay, so we said, well, maybe we can modify these things by going to, electron withdrawing and donating groups. And so if we just, in our minds, make a molecule like this, and it turns out that this does exist, then you can actually tune the reaction profile so that it's more symmetric. And we also functionalize the imidazole a little bit to enhance its reactivity. And we see that these reaction profiles are tunable. So you now get a nice low barrier, double minimum potential, indicating reversible proton exchange. Same thing if you do an aminoimidazole. It's very, very tunable. The problem is, although this molecule exists, this functionalized quinone, it's not soluble in our mixtures. So, that's something that we'll need to think about. And we are thinking about some different species that can go in there. So let me sort of take you through conclusions and next steps, right? So first of all, we've been able to realize this idea of an electrolyte solvent in which charge transport dynamics, kinetics are really disconnected from the solvent dynamics. We saw the importance of both local and non-local nuclear quantum effects. And we now have this nice protocol for generating these AI-driven quantum molecular simulations. Now, one thing that we may want to do is to try to go to higher levels of ab initio theory, better functionals. We actually have done some comparisons of different properties for different functionals, both GGA, hybrid, and meta-GGA. And, amazingly enough, you sort of get, well, with densities, like, for example, you get good performance from R2 scan, which is a meta-GGA, but then you look at diffusion coefficients and conductivities, and it's not so good. And it turns out that sort of the best performing functional, much to our chagrin, is this old B-lib functional. This, apart from the density, but these are all very close when you look at the scale here. But in terms of dynamics, diffusivities, and conductivities, it's kind of doing the best. So that's something that, we may have to just face going forward, that, it's not always the most sophisticated functional that's going to give you the best results. All right. Now, we said we wanted to enhance conductivity. We do. And we're thinking of some different acids. For example, malonic acid is a good one. It's a diprotic acid. We're looking at formic acid, which is another one that we think can enhance the conductivity. But we totally expect these charge transfer mechanisms to be about the same. Of course, we want to continue to develop machine learning potentials for solvating these redox-active molecules. And here are some new redox-active molecules that we're looking at that we think will have better solubilities in these solvents. For example, phenazine, all right, where you have the hydrogen bond donor and acceptors, a nitrogen, an anthraquinone, a quinone core with these imidazole functional groups on the end might solvate better, or take a phenazine core, a pyrazine core with these imidazole functional groups. And initial electrochemical measurements suggest good reversibility so far for phenazine, which is a very interesting one. And, so that's one that we're starting with. And we do have a good machine learning model for, kind of getting the solvation. So there's what the G of R looks like. And we're now studying the solvation-free energies to see how that does. Okay. But now let's talk about charge transfer a little bit, where we're going with that, and then the interface problem. So we like path integrals. And we want to now look at a path integral-based charge transfer method for the electron transfer problem, right? Now, the Hamiltonian looks like this, and, you can kind of picture the situation as you've got two diabatic surfaces. There's maybe some difference between the two minima, and you want to look at the transfer of the electron from the donor to the acceptor. And what that means is you have to calculate a quantum time correlation function, which is one of the most difficult things that you can do. All right. So we've been working on an approach that looks at a kind of slightly modified correlation function called the symmetrized correlation function. And we can relate that to the original one in Fourier space with this simple but rather nasty prefactor here. But the way that we approach this is to say, okay, here's a ring polymer. Half of it represents propagation forward on the acceptor surface. Half of it represents backward propagation on the donor surface. And if we integrate out the path differences formally, we can get a path integral along these R coordinates, which are the averages of points along the forward and backward paths, and that's an open chain path integral. Now, practically, we can integrate over the S's by simply expanding the potential, assuming the S's are small, you go out to second order, and it becomes a Gaussian integral. And so the correlation function amounts then to sampling a kind of potential of mean force, or its real part, because it also gets complex components due to the fact that the donor and acceptor Hamiltonians are different. But it turns out you can actually converge a weighted average like this, even with this phase factor. And second order, you get good results. So if we, like I said, we applied this on the spin boson model, which is a harmonic model, so this approach should be exact, but you can check the numerics of it. So what we did was we took a spin boson model and we took 19 Bath modes. Everything is treated quantum mechanically here, so it's like mimicking nuclear quantum effects. And you can see that the correlation functions for high and low temperature are nicely reproduced over many decades. Especially at low temperature, you can really get the whole thing. In order to kind of get the edges, we have to apply a convolution filter, but this is not really a big problem. And if you look at the actual rate constants versus the energy separation between the donor and acceptor, and compare, for example, to Marcus theory, which is the gold curve, you can see Marcus theory really misses quantitatively what's going on. And that's because it doesn't include nuclear quantum effects. But compared to the Fermi golden rule, our approach is reproducing it really, really, really nicely. Okay, so we want to now expand this out to real molecular systems, and we're working on how to do that. And then the last thing I'll talk about is, okay, now finally we get to interfaces. And a kind of, what we want is a way of kind of ranking different surfaces for their charge transfer characteristics, right? And so we've been looking at a Green's function approach to this, and it actually turns out to be pretty efficient. Now, the inspiration for this comes from the fact that you really want to do the dynamics using a kind of driven Liouville von Neumann type of approach, but that's expensive, right, to solve the Liouville equation and all of this. But, a Green's function picture inspires you to think of things in terms of a kind of energy states approach rather than individual atoms and molecules on a surface. So we imagine a Hamiltonian with the surface and the molecule and then coupling potentials between them. And what you're really after here is the so-called retarded Green's function between, fermion annihilation and creation operators. And we're going to evaluate this in energy space. So you do a Fourier transform and look at this in energy space. And when you do it, you get, a Green's function that looks like this, all right? And what needs to go in here, because this is now being viewed as an open quantum system, is something called the self-energy. And that comes from the molecule surface coupling and the surface Green's function. And it has two components. It has a shift operator and a broadening operator. And the shift is going to tell us about the barrier to electron transfer, and the broadening is, of course, going to tell us about the lifetime of a given state. Okay, so this surface, this self energy, of course, is going to come from the specific surface characteristics, but we're kind of coarse graining it out and treating the molecules on the surface as if they're in contact with kind of an electron bath. So you get, in the end, a non-Hermitian Hamiltonian involving the molecule and this self energy. And so, when you look at the Green's function and you want to get its poles, you would need to solve a set of equations like this. They're kind of nonlinear. the shift and the broadening are going to come from a model of the self energy. And of course, the eigenvalues that you get could come from any method you want. You could use tight binding, or you could use density functional theory, wherever you want to get them. The tricky part, of course, is making sure that you get the ordering right as you turn on this self energy. So what we do is we turn it on adiabatically so that we can watch, like which is the HOMO level, which is the LUMO level, and what happens to these levels as we slowly turn on our self energy function. Okay, so far we've tested this on a simple Newton-Anderson model, which is essentially an extended Huckel or tight binding type model with a Hamiltonian like this. We have a set of hopping integrals, and we get curves that look like this, all right? So this is an analytically solvable model, all right? So everything that we get here is going to be exact, but I can illustrate how the model works. So your self-energy looks like this, so you break it up into its real and imaginary components. The imaginary part is the blue curve, the green is the imaginary part, the real part, the shift. And so if I set some hopping integral values, what you see, well, let's say different molecular hopping integral values, you can look at, the black and the red curves, which are the HOMO and the LUMO of the molecule, and you can look at the shift that you get. Okay, so for example, in this case, you would solve these equations that I showed on the previous slide by kind of, taking a line that's this E minus the eigenvalue, and then looking where it intersects your shift curve, which is the solid curve, and you get a shift, the black circle for the HOMO and the red circle for the LUMO, and you can see that these guys are actually, their shift is negative because you're in the negative region here, and it's positive for the HOMO. And then if you follow the line straight up, you get the actual broadening value. Okay, and depending on the molecule coupling, that shift can go either up or down. For example, if we strengthen the molecule hopping integral, now the shift becomes positive for the HOMO and negative for the LUMO. Very interesting. Okay, and we can look at, many molecular energy levels and get curves like this. I won't go into details, but to show you that you can do it. We've also done it now for a molecule on a Newton-Anderson type surface, so instead of a line of atoms, you have a whole surface. The parts of your self-energy look a little different in this case. I'm sorry about the quality of this, but you can see that, they kind of look a little different. But you can still get your shifting and your broadening values, same procedure. And, you can kind of see, again, how the magnitude of the molecule hopping integral affects it. Now, last thing is we can compare this to different approximations. This is my last slide. So if I do like a wide band limit approximation where I just set the components of the self-energy to be constant at all energies, and what we're looking at here are the poles of the Green's function, so the real and imaginary parts, for different different molecule hopping integrals ranging from minus 0.8 up to 0.2, and different surface molecule couplings ranging from 0 down to minus 0.8. and you can see the HOMO and the LUMO shifts. And, you know, the using the proper self-energy gives you the right behavior that you can't really reproduce with this wide band limit or this other approximation, which I don't know what you call it, but, you know, basically you take a step for the broadening part and a curve that looks like this, very different from the real one for the shift part. It's really not that different from the wide band limit. So you really want to be doing these things within a proper representation of your self-energy. Okay, so I think I'm really out of time, so I'm going to finish up here. And just to say that, you know, we want to continue to develop these path integral and Green's function schemes so that we can really look at these charge transfer reactions occurring in the liquid and, of course, at the interface. And so we're looking forward to these developments and how they're going to affect our forward work. So it's a good place for me to stop. Thanks, everyone, for your attention, and I'm happy to take any questions.